Thank you very much for the very kind opportunity to present my research in this session, which is collaborative with Frederic Muzeng from INRIA in France and also Miroslav Kristich from UC San Diego, and pertains to a new class of soup delay inequalities, which provide a variant of Hellene's inequality, which we have found to be useful for proving asymptotic stability properties for switch systems and also for continuous discrete systems, which we believe were beyond the scope of the literature. And this is based on a recently appearing paper in LCSS and has been supported by grants from the U.S. National Science Foundation, for which we are very much appreciative. I will start with a general overview of soup delay inequalities and a summary of our work, which we will get to in more detail later. And I begin by the standard contraction or contractivity type conditions for non-negative valued functions v, which posits the existence of two constants, an epsilon on the open interval 0, 1, and a real value, capital T, in fact, a non-negative value, such that the condition so indicated is true for all large enough little t. And here the right-hand side term involving the vertical lines refers to the supremum of V on that interval, little t minus capital T up to little t, and therefore we call such inequalities soup delay inequalities. But these are standard ones, and proving them for suitable V is actually useful in some cases for proving stability properties, as has been demonstrated in works by Hütte, Osbey, and Said Ahmed and others in the context of switched systems. On the other hand, a related type of soup delay inequality is the so-called Helenic inequality, which has been widely used by Amelia Friedman and her co-workers in numerous opportunities and applications. And here we have the existence of two constants C and little a, two positive constants, and again a supremum on the right-hand side. And in the special case where the gain constant C is strictly less than the decay rate little a, it turns out that the Helenic inequality is of a classical type that helps prove contractivity, which in turn can help prove asymptotic stability properties. But our revised or relaxed version of the contraction conditions has the following form, where there are now, in addition to the epsilon on the interval 0, 1, we also have additional constants, tau upper and tau lower bar, and a function rho of t, which will satisfy certain conditions that we will get to soon enough. And it turns out that for suitable functions rho and for suitable constants epsilon, this relaxed contraction type condition holds under relaxed Helenic inequality, and they also have relaxations that will allow cases where C of t is strictly larger than A, insofar that there are non-standard versions of Helenic inequality which are satisfied under our relaxed contractivity condition, and thereby can be used for proving stability properties for systems with switching delays, as well as continuous discrete systems and other applications. And here is a partial list of people who have worked on related issues. Osbey and Said Ahmed have applied contractivity type conditions in the context of switch systems, and Friedman has used Helenic inequality for various applications with Selivanov and Pierdomenico Pepe. And I emphasize, though, that we believe that our generalized soup delay inequalities are useful for covering cases of dynamical systems where we have to prove asymptotic stability, but which were beyond the scope of earlier results. Now I turn to the main assumptions of our work. Here is our relaxed contractivity condition with an added eta of t, and here are our conditions. We assume that the rho is a non-negative valued function which has a known bound rho bar, and that eta also is piecewise continuous, and we have constants, not only the tau lower and upper bar, but also a constant omega on the open interval 0, 1, and a positive integer capital N, such that two conditions are satisfied, namely 1 and 2, and condition 1 has a product on the left side a product of capital N plus 1 terms, each of which is a supremum of the row on certain intervals. And this condition 1 is required to hold for all large enough little t, as well as a condition on capital omega that you see in 2, which has a interpretation that even though the right hand side of that equality in 2 has a sum which can have many terms, it still needs to be the case that capital omega is small enough. And a way to interpret the condition 1 is that rho is required to be small enough in an average sense. The point being that it could be that the rho bar, the upper bound on rho that you see in this second line, is larger than 1, but it must be the case that the times when the rho is small compensate in some sense for the times when rho is large in order to have a product which is less than or equal to some value omega that is strictly less than 1. And an interpretation of condition 2 is that the bigger rho bar is, the smaller the epsilon has to be in some sense in order to ensure that this capital omega is on the open interval 0, 1. And it turns out that this capital omega will be used to give us a rate of convergence of v to 0. In fact, it is minus ln of capital omega over a suitable constant, which will be our rate of convergence in our theorem, which I will turn to next. So we maintain our assumptions on the rho and the epsilon that we had in the previous slide, and I assume that v and eta are locally bounded piecewise continuous functions that satisfy our relaxed contractivity condition from the earlier slide for all little t larger than or equal to 0. And our conclusion is that we have a kind of exponential ISS result, namely a sum of 2 terms as an upper bound on the v, the first of which is converging to 0 exponentially fast, and the second one is not necessarily doing so. And here we see, therefore, that there is a rate of convergence that depends on the little omega and also the rho bar and the epsilon, namely the capital omega is present in the exponential in the first term on the right-hand side of 3, and the rate of convergence, therefore, is minus ln of capital omega over tau bar, and also times capital N plus 1 in the denominator. And so this says that the v converges exponentially fast to 0 in an exponential ISS way with an overshoot depending on the supremum of the eta. A remark that's worth noting is that even though we allow the rho bar and therefore also the rho of t to take values strictly larger than 1, it is not possible to drop the assumption that epsilon is strictly less than 1, because there exist unbounded functions v that satisfy all the assumptions of this theorem with eta is equal to 0, except that the epsilon is larger than 1. And therefore, that would violate the conclusion of the theorem if v is unbounded. And it is in this counter example that I described. And therefore, this explains that if the condition that epsilon is strictly less than 1 is not present, then we would not be able to prove the same exponential stability result. That is, that assumption cannot be dropped, because under the remaining assumptions, we can find unbounded v's that satisfy the assumptions of the theorem with a 0 eta, but therefore would not satisfy the conclusion of the theorem. Let me turn next to how what this theorem says is related to the generalized Hellenic inequality. So recall that in the classical Hellenic inequalities, we have a constant gain, but here in the generalized ones, we can have a C of t, a gain that depends on t, and which can take some of its values strictly larger than this little a. And we can rearrange this generalized Hellenic inequality to obtain a soup delay inequality with an epsilon equal to 0 with suitable scalings of the time horizon, where you are taking the supremum on the right side and for a certain choice of the eta. and the eta, in fact, is 0 in this case, and the rho of t is what you see in the second line, and we can find conditions on the c of t and the a such that this rho satisfies the requirements of the previous theorem with epsilon equals 0 and eta equals 0 in a way that allows us to cover generalized inequalities of the Helene type that were beyond the scope of earlier Helene inequality applications. In terms of other applications, we have applied our theorem to LTI systems with switch delays, capital D of t, that are piecewise continuous and which satisfy a suitably small bound on some intervals where Helene's inequality in the usual classical sense holds. And then we put conditions on the allowable lengths of the other intervals using our earlier result, namely the theorem that we alluded to previously. And we also have results for continuous discrete systems, which we believe were consequences of our theorem, which were not previously available in the literature. In terms of other applications that we can cover, we have also applied our generalized soup delay inequalities to observer design, which are beyond, or which is beyond the scope of this talk, but I will instead point you to this paper of ours that also appeared this year in Automatica. So to summarize what we did, we have generalized the usual contractivity type inequalities in order to introduce additional right-hand side terms such as what you see in this second inequality here, where you have a supremum over some interval, and in so doing, we have conditions that are satisfied under generalized Helene's inequalities, and these generalized Helene's inequalities arise in the study of switch systems and other key applications to which we believe that our results could have a positive impact. And with that, I will close, and thank you very much for your very kind attention.